This article describes the calling conventions used when programming X86 architecture microprocessors. Calling conventions describe the interface of called code, the order in which atomic parameters, or individual parts of a complex parameter, are allocated, how parameters are passed, which registers the callee must preserve for the caller, how the task of preparing the stack for, and restoring after, a function call is divided between the caller and the callee. This is intimately related with the assignment of sizes and formats to programming language types. Another closely related topic is name mangling, which determines how symbol names in the code map to symbol names used by the linker. Calling conventions, type representations, and name mangling are all part of what is known as an application binary interface. There are often subtle differences in how various compilers implement these conventions, so it is often difficult to interface code which is compiled by different compilers. On the other hand, conventions which are used as an API standard are very uniformly implemented. Historical background: prior to microcomputers, the machine manufacturer generally provided an operating system and compilers for several programming languages. The calling convention, S, for each platform were those defined by the manufacturer's programming tools. Early microcomputers before Apple II computers generally came bare of an OS or compilers, as did the IBM PC. The only hardware standard for IBM PC-compatible machines was defined by the Intel processors and the literal hardware IBM shipped. Hardware extensions and all software standards were thrown open to market competition. A multitude of independent software firms offered operating systems, compilers for many programming languages, and applications. Many different calling schemes were implemented by the firms, often mutually exclusive, based on different requirements, historical practices, and programmer creativity. After the IBM-compatible market shakeout, Microsoft operating systems and programming tools predominated, while second-tier firms like Boolean and Novell, and open-source projects like GCC, still maintained their own standards. Provisions for interoperability between vendors and products were eventually adopted, simplifying the problem of choosing a viable convention. Caller cleanup: in these conventions, the caller cleans the arguments from the stack, which allows for variable argument lists. For example, printf. Cdecl: the Cdecl is a calling convention that originates from the C programming language and is used by many C compilers for the X86 architecture. In Cdecl, subroutine arguments are passed on the stack. Integer values and memory addresses are returned in the EAX register, floating point values in the STOX87 register. Registers EAX, ECX, and EDX are caller saved, and the rest are callee saved. The X87 floating point registers STO to ST7 must be empty when calling a new function, and ST1 to ST7 must be empty on exiting a function. In context of the C programming language, function arguments are pushed on the stack in the reverse order. In GNU Linux, GCC sets the de facto standard for calling conventions. Since GCC version 4.5, the stack must be aligned to a 16-byte boundary when calling a function. Consider the following C source code snippet. On x86, it will produce the following assembly code. The caller cleans the stack after the function call returns. There are some variations in the interpretation of Cdecl, particularly in how to return values. As a result, x86 programs compiled for different operating system platforms and or by different compilers can be incompatible, even if they both use the Cdecl convention and do not call out to the underlying environment. Some compilers return simple data structures with a length of 2 registers or less in the register pair EAX, EDX, and larger structures and class objects requiring special treatment by the exception handler are returned in memory. To pass in memory, the caller allocates memory and passes a pointer to it as a hidden first parameter. The callee populates the memory and returns the pointer, popping the hidden pointer when returning. In Linux GCC, double floating point values should be pushed on the stack via the x87 pseudo-stack. Like so. Using this method ensures it is pushed on the stack in the correct format. The Cdecl calling convention is usually the default calling convention for x86C compilers, although many compilers provide options to automatically change the calling conventions used. To manually define a function to be Cdecl, some support the following syntax. The Cdecl modifier must be included in the function prototype and in the function declaration, to override any other settings that might be in place. Syscall, this is similar to Cdecl in that arguments are pushed right to left. EAX, ECX, and EDX are not preserved. The size of the parameter list in double words is passed in AL. Syscall is the standard calling convention for 32-bit OS/2 API. Optlink, arguments are pushed right to left. The three lexically first arguments are passed in EAX, EDX, and ECX, and up to 4 floating point arguments are passed in street 0 through street 3, although space for them is reserved in the argument list on the stack. Results are returned in EAX or street 0. Registers EBP, EBX, ESI, and EDI are preserved. Optlink is used by the IBM Visual Age compilers. Cali cleanup. When the Cali cleans the arguments from the stack, it needs to be known at compile time how many bytes the stack needs to be adjusted. Therefore, these calling conventions are not compatible with variable argument lists, for example printf. They may be, however, more space efficient, as the code needed to unwind the stack does not need to be generated for each call. Functions which utilize these conventions are easy to recognize in ASM code because they will unwind the stack prior to returning. The x86 ret instruction allows an optional 16-bit parameter that specifies the number of stack bytes to unwind before returning to the caller. Such code looks like this. Pascal, based on the Pascal programming language's calling convention, the parameters are pushed on the stack in left to right order, and the Cali is responsible for balancing the stack before return. This calling convention was common in the following 16-bit APIs, OS/2 Microsoft Windows 3X, and Ball and Delphi version 1X. Modern versions of the Windows API use Syscall, which still has the Cali restoring the stack as in the Pascal convention, but the parameters are now pushed right to left. Register, an alias for Ball and Fastcall, Syscall. The Syscall calling convention is a variation on the Pascal calling convention in which the Cali is responsible for cleaning up the stack, but the parameters are pushed onto the stack in right to left order, as in the Cdecl calling convention. Registers EAX, ECX, and EDX are designated for use within the function. Return values are stored in the EAX register. Syscall is the standard calling convention for the Microsoft Win32 API and for OpenWRTSOM C++. Fastcall, conventions entitled Fastcall have not been standardized, and have been implemented differently, depending on the compiler vendor. Typically Fastcall calling conventions pass one or more arguments in registers, which reduces the number of memory accesses required for the call. Microsoft Fastcall, Microsoft or GCC Fastcall convention passes the first two arguments that fit into ECX and EDX. Remaining arguments are pushed onto the stack from right to left. When MIS compiler compiles for IA64 or 64 Armenian DRAMs, it ignored the Fastcall keyword and uses the 164-bit calling convention instead. Ball and Fastcall, evaluating arguments from left to right, it passes three arguments via EAX, EDX, ECX. Remaining arguments are pushed onto the stack, also left to right. It is the default calling convention of the 32-bit compiler of Embarcadero Delphi, where it is known as register. Some versions of Linux kernel use this convention on i386. WRTSOM register-based calling convention. WRTSOM does not support the Fastcall keyword except to alias it to null. The register calling convention may be selected by command line switch. Up to 4 registers are assigned to arguments in the order X, EDX, EBX, ECX. Arguments are assigned to registers from left to right. If any argument cannot be assigned to a register, it, and all subsequent arguments, are assigned to the stack. Arguments assigned to the stack are pushed from right to left. Names are mangled by adding a suffixed underscore. Variadic functions fall back to the WATSUM stack-based calling convention. The WATSUM C++ compiler also uses the pragma-o directive that allows the user to specify his own calling convention. As its manual states, very few users are likely to need this method, but if it is needed, it can be a lifesaver. Top speed /clarion/JPI, the first four integer parameters are passed in registers X, EBX, ECX and EDX. Floating point parameters are passed on the floating point stack Euro registers STO, ST1, ST2, ST3, ST4, ST5 and ST6. Structure parameters are always passed on the stack. Additional parameters are passed on the stack after registers are exhausted. Integer values are returned in X, pointers in EDX and floating point types in STO, Safecall, in Embarcadero Delphi and Free Pascal on Microsoft Windows. The Safecall calling convention encapsulates COM error handling, thus exceptions aren't leaked out to the caller, but are reported in the result return value, as required by COM-OLE. When calling a Safecall function from Delphi code, Delphi also automatically checks the returned result and raises an exception if necessary. The Safecall calling convention is the same as the Syscall calling convention, except that exceptions are passed back to the caller in EAX as a result, while the function result is passed by reference on the stack as though it were a final out parameter. When calling a Delphi function from Delphi, this calling convention will appear just like any other calling convention, because although exceptions are passed back in EAX, they are automatically converted back to proper exceptions by the caller. When using COM objects created in other languages, the results will be automatically raised as exceptions, and the result for get functions is in the result rather than a parameter. When creating COM objects in Delphi with Safecall, there is no need to worry about results, as exceptions can be raised as normal but will be seen as results in other languages. Returns a result and raises exceptions like a normal Delphi function, but it passes values and exceptions as though it was either caller or callee cleanup. This calling convention is used for calling C++ non-static member functions. There are two primary versions of this call used depending on the compiler and whether or not the function uses variable arguments. For the GCC compiler, this call is almost identical to Cdecl. The caller cleans the stack, and the parameters are passed in right to left order. The difference is the addition of the this pointer, which is pushed onto the stack last, as if it were the first parameter in the function prototype. On the Microsoft Visual C++ compiler, the this pointer is passed in ECX and it is the callee that cleans the stack, mirroring the Syscall convention used in C for this compiler and in Windows API functions. When functions use a variable number of arguments, it is the caller that cleans the stack. The Syscall calling convention can only be explicitly specified on Microsoft Visual C++ 2005 and later. On any other compiler, Syscall is not a keyword. Register preservation, another part of a calling convention, is which registers are guaranteed to retain their values after a subroutine call. According to the Intel ABI to which the vast majority of compilers conform, the EAX, EDX, and ECX are to be free for use within a procedure or function, and need not be preserved. X86-64 calling conventions. X86-64 calling conventions take advantage of the additional register space to pass more arguments in registers. Also, the number of incompatible calling conventions has been reduced. There are two in common use. Microsoft X64 calling convention. The Microsoft X64 calling convention is followed on Microsoft Windows and pre-boot UEFI. It uses registers RCX, RDX, R8, R9 for the first four integer or pointer arguments, and XMMO, XMM1, XMM2, XMM3 are used for floating point arguments. Additional arguments are pushed onto the stack. Integer return values are returned in array X if 64 bits or less. Floating point return values are returned in XMMO. Parameters less than 64 bits long are not zero extended. The high bits are not zeroed. When compiling for the x64 architecture in a Windows context, there is only one calling convention, the one described here, so that Cdecl, Syscall, Cdecl, fastcall, etc., are now all one and the same. In the Microsoft x64 calling convention, it's the caller's responsibility to allocate 32 bytes of shadow space on the stack right before calling the function, and to pop the stack after the call. The shadow space is used to spill RCX, RDX, R8, and R9, but must be made available to all functions, even those with fewer than 4 parameters. For example, a function taking 5 integer arguments will take the first to fourth in registers, and the fifth will be pushed on the top of the shadow space. So when the called function is entered, the stack will decompose the return address by the shadow space followed by the fifth parameter. In x86-64, Visual Studio 2008 stores floating point numbers in XMM6 and XMM7. Consequently, for x86-64, user-written assembly language routines must preserve XMM6 and XMM7. In other words, user-written assembly language routines must be updated to say restore XMM6 and XMM7 before after the function when being ported from x86 to x86-64. System VAMD64 ABI. The calling convention of the System VAMD64 ABI is followed on Solaris, GNU Linux, FreeBSD, Mac OS X, and other Unix-like or POSIX compliant operating systems. The first 6 integer or pointer arguments are passed in registers RDI, RSI, RDX, RCX, R8, and R9, while XMMO, XMM1, XMM2, XMM3, XMM4, XMM5, XMM6 and XMM7 are used for floating point arguments. For system calls, R10 is used instead of RCX. As in the Microsoft x64 calling convention, additional arguments are passed on the stack and the return value is stored in array X. Registers RBP, RBX, and R12 or 15 are Kali save registers. All others must be saved by the caller if they wish to preserve their values. Unlike the Microsoft calling convention, a shadow space is not provided. On function entry, the return address is adjacent to the 7th integer argument on the stack. List of x86 calling conventions. This is a list of x86 calling conventions. These are conventions primarily intended for C++ compilers, and thus largely special cases. Other languages may use other formats and conventions in their implementations. References: System V Application Binary Interface Intel 386 Architecture Processor Supplement. The Santa Cruz Operation, Incorporated March 19, 1997 Nemanja Trifanovic. Shauna Wington, ed. Calling Conventions Demystified. The Code Projector, Stephen J. Friedel. Intel x86 Function Call Conventions Assembly View. Steve Friedel's UnixWiz.net Tech Tips. Visual Studio 2010 Visual C++ Calling Convention. MSDN Library. Microsoft. 2010 Andreas Johnson. Calling Conventions on the x86 Platformer, Raymond Chen. The History of Calling Conventions, Part 1 Inch. The Old New Thing, Raymond Chen. The History of Calling Conventions, Part 2 Inches. The Old New Thing, Raymond Chen. The History of Calling Conventions, Part 3 Inches. The Old New Thing, Raymond Chen. The History of Calling Conventions, Part 4, Year 64. The Old New Thing, Raymond Chen. The History of Calling Conventions, Part 5. AM64. The Old New Thing, Further Reading, Jonathan Du Bois Pollard. The Gen on Function Calling Conventions. Frequently Given Answers, Kip R. Irvine. Advanced Procedures. Assembly Language for x86 Processors. Prentice Hall. ISBN A978-0-13-600-2212-1, Ball and C++ version 3.1 User Guide. Borland 1992 PPA 158189 Euro 191 Thomas Lauer. The new Syscall calling sequence. Porting to Win32, a guide to making your applications ready for the 32-bit future of Windows. Springer. ISBN A978-0-387-94572-9A